Absolutely not. Has nothing to do with reality. If you haven't got it, get a copy. It's fun to go through. All right. So what do we touch on? Relativistic mass, right? This idea that as matter or mass approaches the speed of light, the mass goes to infinity. Wrong. Lorentz factor. Wrong. The fact that you have to look at, what I said here, every physical system has an absolute operational finite upper bound. That's what actually takes place. And we're going to see how technology plays into that, right? So you can't look at an accelerator or collider saying that it can only accelerate a particle up to, less than the speed of light, and therefore it's a bound. It's not. It's a technological mental bound. That's all. All right, so off we go to another one. So I have this, and this is just kind of showing you what I'm talking about. So this is example one. You have the rest mass of an electron over here, right? And I just have it 9.10939 times e to the negative 31 kilograms, okay? And then if you accelerated that electron up to 0.9999999 or whatever, right, you get a Lorentz factor of 22,361, or 2,236,068%, saying the mass goes up by that percent. But the actual mass, of the electron, going at that speed, just below the speed of light, right, and you end up with 2.37042 e to the negative 26th. So here you are accelerating a particle up to just below the speed of light, which this says it gains mass, but when you look at what the mass change is, there's nothing there. It's statistically zero, right? And if you take example here, accelerate to 500 million %, what you end up with is 4.55468 times e to the negative 24th kilograms. It's the same idea. Statistically, there's nothing there, right? So this idea that mass grows up into becomes infinite, it's not even close to reality. So, you can look at that in relation to that and sort of see what's going on. Here's the important part, right? So, here you have basically the same idea, where you have a graph like before. I put input on the vertical axis, and I put output. Here's output. I put output on the horizontal axis. I just carried it off over here. But if you look at behind this, you see the curvature of the mass increasing. Well, you see it down here too. It's the same basic idea, except you have this technological factor in here, which you can see kind of runs through this technology, runs through this whole area. So it's not so much that this has, if we take it from this point, and you say force and energy over here and speed over there, whatever, you can put whatever you want to notate it as. But you'll see that this is similar to this, right? But it's finite, right? It goes up, it increases maybe, the inputs, he's saying mass there, but the idea here, input goes up, right? It'll get at that point, but it's finite. It's not infinite like it goes up here. But then what happens? It's not so much that it just stays there, it's that technology within the system, and what happens? It follows a different track, X years later, whatever that may be, right? And then even from that, it goes to a finite bound, but then what happens? Then technology enters the system, and it pushes all these, what we would call barriers before. It takes and pushes all these barriers forward, and so now the speed is greater, right? depending on what the energy input is. But it's also a standard. It's also a fixed point, right? It goes up there. That's the fixed point per unit time. Wait 20 years, it'll push out again. So that's how it works, right? We sort of have a technology. We go as fast as we can. It goes up to a certain point up here, whatever, and we have a output down here, speed or whatever like that, and for the time being, it stays here, except technology keeps pushing forward. So this doesn't work, but this works. That's how you can. Right now, we're sort of stuck with the accelerator, perhaps out here, but eventually we're going to find a way to get past that, right? I mean, new technologies are different. Here's sort of a. Oh yeah, here's one of my adages. Math is not a substitute for thinking. I'm beyond that. I mean, if you've seen any of my videos, I mean, this is the way I present them. I mean, the math is pretty much, high school math of that. But it's the concept that's important, right? I mean, if the concept is right, the math will follow. You'll see that again. So math is not a substitute for thinking. And if you look here, these are some colliders, accelerators. I think this is the Fermi as to what it can, the energy. So it's 1 tera electron volt. And here's the European synchrotron. That's 6 giga electron volts. And here's the Stanford accelerator or collider, and that's 50 giga electron volts. And then you have the CERN Large Hadron Collider, 6.5 tera electron volts, right? So over time, I mean, these are the older ones. This is the sort of the newer ones, right? Well, what changed? Well, technology, right? The speed of light doesn't change, or the upper bound acceleration changes, but it's small, right? But the energy you put into the system, that's a lot bigger, right? And that's what? Technology. So remember this too, math is not a substitute for thinking. You have to still think. You can't just let math, run amok and make your conclusions for you. And this one, I think we got it. So here's what I was saying before, another little adage. If the concept is correct, then the math will follow. The reverse isn't true, right? Too much I see, and I think it might be starting to change. Everybody, leads with mathematics, trying to make mathematical formula or mathematical equations and sort of make unclear choices to connect those equations together and end up with something that's totally wrong, right? So if the concept, the underlying concept, physical concept is correct, the math will follow, right? The reverse is not true. One thing about the, what I was talking before about technology, and it's always been this way, right? Oh, we can't do that, it won't work, we can't, And somebody, the ones that are sitting around groping or griping that, it won't work, and they sit there and God knows what they do, but, somebody comes along and, finds a way. It's always the way it works. So here we have some examples, real world examples, right? So a long time ago, back in the 50s, maybe 40s, maybe earlier, people thought in athletics, and especially running, that nobody would be able to break the 4-minute mile. Right? I mean, many people tried to do it, and they couldn't do it. Close, but they could never do that. And yet in 1954, a man by the name of, now it's Sir Roger Bannister, did break the he was British, did break the 4-minute mile with a time of 3 minutes, 59 seconds, and 4/10. He just made it, but he made it. And what's happened since? Now the current record for the mile is 3 minutes, 43 seconds and 13 100ths. So, I mean, that's like 16 seconds taken off Roger Bannister's original number. So, and that's a lot. And we go back and look at the 1908 Model T Ford, right? It could go at like 45 miles an hour, right? And it's pretty interesting if you ever see inside one, because the fuel, there isn't a fuel pump, it's a fuel drop. They have the fuel up high, just dripping into the engine, whatever. But now a stock car, the fastest stock car, like in the NASCAR circuit, was trying for the position in the race, was 213 miles an hour. You know, so 213 miles an hour minus 45 miles an hour. I mean, that's a big change in technology, right? And then Wright brothers, right? The Wright brothers' initial, well, first flight in 1903, a plane under its own power, right, was about 30 miles an hour, and I think it went like 120 feet. I mean, that was the 1903 first flight of the Wright brothers at Kitty Hawk with an airplane under its own power. So that was about 30 miles an hour and went 120 feet. And then what you have is sort of the plane that I like, or I don't know exactly, maybe it has a different technique name than that, but it is the SR-71 Lockheed Blackbird, right? And I think you've probably all seen this. It's pretty, it has a very interesting shape to it. I mean, it's a great looking plane, and it had a top speed of Mach 2, right? So it was Mach 2, 2.86, and that's roughly about 2,200 miles an hour, right, for that one plane. I don't know, plane, jet aircraft, I mean, whatever. And I know they used it during the Vietnam War. They would fly over the north or whatever, and that would set off the missile batteries, anti-aircraft missile batteries in the north, and they'd shoot at it, but they couldn't hit it, because by the time it got to the space where they could try and hit it, they ran out of fuel, and the missiles just fell to the ground somewhere. So that's pretty interesting. Now, so here let me just sort of reiterate what I've talked about before, right? A mass does not reach infinity as the velocity approaches the speed of light. The speed of light is, again, not a barrier. It's not a physical